Okay, hi everyone. This is my video number 8. Okay, so for today's video, I would like to talk on tangential and normal component of the acceleration. Yeah, tangential and normal components of acceleration. Okay, so what is this means? What does this mean? So it means that for a given vector r, okay, a function of t, of course we can find v, which we differentiate those, the r dt, and from that we can find a by differentiate v t. All right, all these are vectors. So now we want to write a instead of just dv dt, where in this case you may depend on component for I, component for j, component for k. All right, this thing. Now we do want this. What we want to do now is we want to write. So what we want to write is we want to write a in terms of tangential component. We have something like that plus a normal components. Yeah, so that's what we want to write. Okay, now we need to find what is at, what is nt. So that's our purpose. Now if we define or we already know this thing actually, v as a magnitude of v, where this one is v with bar there, this is a vector and magnitude, and this is just a scalar. So right, and by definition we define tangent as r prime over magnitude of r. Okay, and then this is r prime is v, and r prime, magnitude of r prime, this is magnitude of v prime. So you can write this as that one is v vector, and this using that. So where this is v. Okay, so consider this equation here. Consider that equation. We can write v. So therefore we have v is equal to vt. Okay, now in order to get a from that v, we just differentiate those things. So we differentiate v. So we have, if you differentiate v, we have a. Now to differentiate this, you use the product rule. All right, so we have v prime t plus, you differentiate one, you fix one, you differentiate one, you fix one, the other one. All right, v t bar. Now if you look at the general form from here, and you compare with the general form that we have here, okay, we already have, this is t bar, this is t bar. So at is actually v prime. All right, this is very clear. But this one, a n bar here, but this is t prime. So we need to write this t prime we need to write this t prime in terms of something n bar, vector n. If you can write this, we substitute into that, so we can find an. So that's the purpose now. Now, so let's do this. So how can we relate t prime with other definition that we already know? Okay, so if we use the definition of curvature, all right, the curvature we define curvature as kappa equal to t prime over r prime. Okay, our r prime is given as v, so we just v, so we have t prime over v. So rearrange those. Remember that we want t prime, t. So here in this case, we have t, magnitude of t, this is mu k, mu kappa, curvature. But again, the normal vector n, is defined as t prime over magnitude of t prime. That. So I can write the magnitude of t prime. As the vector t. We can write the vector t that as a t n. Okay. From there we have this thing. But t prime here is given here. Given that. So I can write this as a mu kappa n. Okay. So therefore, if I can give this equation star, okay, if I can give equation star, let's call this equation star. All right. So from star, we have okay, A is equal to v prime t plus kappa v squared n. Okay, so from here, of course, we can write this as a t plus n, where at is equal to v prime, an is equal to kappa mu square. Okay, so this formula or this expression shows that the acceleration can be written as a in form of tangential and normal vector with their components. Okay, so that's the first thing. And then the second thing, if you look at this, at v prime an kappa mu at is mu prime, an is kappa mu squared. Sometimes it's not that easy to memorize. So let's try to think, how can we write this in a much simpler form or much more easier way to memorize. Okay, so let me stress again this thing. So if this is our trajectory of some particle, and the acceleration can be written as that. So which means we have a tangent vector is here, we have a normal vector is here, normal vector is here. Remember that the normal vector are always pointed inside the curve, and so A is given as the summation between this. This is normal, so you can, this is your A. Okay, so this is, if you make it a little bit longer there, so this is the AN, this is the AT. Okay, so now let's try to write AT and AN in much simpler form. Okay, so now we want to express AT and AN in term of R prime and R double prime. Okay, so we take the dot product, dot product of let's call this double star. Star, this is double star. Okay, so let's say take the dot product double star, which is that equation with vector velocity mu t. You can use that. Okay, so we take the dot product with that. So what we have, v with a, so we have v dot a, they're equal to, so we have v t dot v prime t, oh sorry, this is without that, plus k squared n. Okay, so we have v prime plus v prime t dot t prime plus kappa that t n. Alright, this one is 0 because t and n is always perpendicular, so dot product with this is 0, and t dot t prime, no, not this prime, tt, so this give you 1. Alright, this give you 1, this one give you 0. So what left is, we have a dot a is equal to v prime. Okay, so therefore AT, our AT is v prime. Okay, this is v prime. So v prime, this is, just use this, look at this, is v prime, you can write this v prime, this is v a dot v. Okay, this is v is r prime, a is r double prime, v is magnitude of r prime. Okay, so therefore AT can be written as that. So we have AT is r prime r double prime r prime prime. Okay, and then for an, we have kappa v square. This is kappa is given as, we have defined this over r q, and then v is those things squared. Okay, so cancel that. What left is r prime r double prime over r prime magnitude. Right. So we have written the component for tangent, unit tangent can be written as that, and the component for unit normal can be written as that for the acceleration. So for the example, I'll give in the next video. Thank you.